Okay, we'll continue where we left off last time. Okay, come on. And we're going to talk today about gradient descent, and if we have time, we'll do some kind of extra examples around gradient descent. I checked and I ran this demo beforehand. It did not crash when I ran at home, so let's hope for the best. I'm also extra sleep deprived today, so please double check my algebra on everything. I'm generally always sleep deprived, but today I'm really sleep deprived. So make sure you're awake to if I make algebra mistakes, please catch them. Okay, so last time we talked about gradient descent on the least squares example. And we basically ended up with the following kind of step, right, at the end, or we showed the following, that xk plus 1 minus A transpose A inverse A transpose B is equal to I minus 2 eta A transpose A whole to the k plus 1 times x naught minus A transpose A inverse times A transpose B. Right? Everyone remember that we did this calculation? And here, basically this is just x star, right? X star is our optimal solution. And so what we did was we said, let's look at how far we are from the optimal solution. And we said that if you start out, at x naught minus x star, then you're going to decay according to the powers of this particular matrix. Does everyone remember that? Okay. And so here what we have now is, again, we have this nice symmetric matrix here. And so what we can do is we know when this is going to converge and when this is not going to converge, right? When this is going to diverge. And what did we say? This depends on what property of this matrix? The eigenvalues, right? And in particular, we want the absolute value, so absolute value of eigenvalues of I minus 2 eta A transpose A to be strictly less than 1. Right? That's what we need for this to be able to converge. Okay? For those of you who attended discussion yesterday, by the way, we put a gradient descent problem on the discussion knowing that some of you will have this lecture after the discussion yesterday, but we wanted to make sure you had a gradient descent discussion problem before the midterm. So that problem was added on discussion yesterday. So if there are aspects of the discussion problem yesterday that were kind of like, not quite clear, this lecture should make all of them clear, okay? But we wanted to make sure you had access to that early, so we kind of put it on a little bit earlier than we would have otherwise done. But now, this is the particular condition we want. And doing the homework problem will, emphasize this and let you see this again. How can we ensure that this is actually possible, right? What is this eta here? This eta is our step size, right? This marker is barely visible. Okay. So what do we have control over to make sure that this is actually possible, right? We have control over eta. And so what you see is that depending on the choice of eta, the eigenvalues of this matrix are going to change, right? And so the key is to make sure that we can choose an eta such that we can actually get this to converge. Okay? Does everyone see that? We have not proved that this converges for any step size eta. Right? We've proved it converges only when this holds. Okay? So now let's look at this in the context of this demo. So here what I'm doing is we have kind of the simplest possible setup. So I have some vector x. So this is the setup. I have some vector x1, x2, xn times some unknown theta is equal to y1, y2, yn. It's a one-dimensional least squares problem, right? So this is my x. This is my true theta is 0.5. And I'm generating some observations y. So and I have some kind of random noise that is added to my observations to be able to generate my sample data. Okay? And now what I'm going to do is let's actually just first look at what our loss looks like, right? So our loss is going to be a quadratic loss, right? It's the least squares loss. And for different values of theta, this is what our loss looks like. And you can see that this is a parabola, as it should be. And what is the minimum point of this? Where is this minimum exactly? 0.5, right? That's our true theta. So you can see it's a little bit offset from 0. That's the... And another way to think about this is that all these black crosses here, these black x's are our data points, which are generated by this y here. And what we want to do is we want to find the slope of that line, right? That's basically what you're doing here. Everyone see that? OK. So let's do this. Instead of doing this by least squares, let's do it by gradient descent. And so what we're going to do is, let's say, set capital N to be the number of steps I take. So here I've set n to be 5. Let's set eta, which is our step size, to be 1. And let's say I start at some initial point, which is -10. Arbitrary initialization, but we're just doing a demo. And what I get is I'm starting here at -10. The first step takes me towards the minimum. The second step takes me closer. Third step takes me closer. In 5 steps, I'm kind of close, but I'm not quite there. And you can see what these values of theta are that are shown here. So you start at -10, and in 5 steps, you're at like -1.5. So 5 steps wasn't enough to converge. What if I took 10 steps? If I take 10 steps, this is kind of my sequence of outputs. Still not quite there, though I'm getting closer. If I take, let's say, 20 steps, I'm getting very close to converging, right? OK? Does everyone see that? So now what might I want to change, right? I'm converging kind of slowly, actually, here. I could converge much faster. So what's a suggestion on how we might converge faster? Anyone? Someone else? I appreciate that you ask questions, but just to get everyone to participate. Change eta, right? Good job. OK, so let's make eta 2, right? Take bigger steps. Let's see what happens. And let's see if I just take, again, start with 5 steps. 5 steps, I've gotten much closer in 5 steps. Now I've doubled eta, right? My last theta is 0.3. What if I make eta 3? If I make eta 3, wow, boom, right? I'm converging much faster. I haven't quite converged, but this is really good. OK? If I was to take, let's say, 10 steps, I'm really going very, very fast, getting pretty close, right? I haven't quite converged yet. A converging would be, really having exactly 0.5. OK, let's try to converge faster. What if I choose eta equal to 5, let's say? Whoa, OK? It's converging, but this might not be what you wanted to be doing, right? Kind of ping-ponging all around the place, but it's not exploding, at least. And now let's try, where's my eta? Let me try, let's say, what if I did eta equal to 8? Whoa. I blew up completely, right? It did not even go towards the minimum. It totally diverged, right? So you can see that basically for some, I've clearly chosen the eta out of bounds that is now making this not want to converge, right? So I could compute, and this is exactly what you'll do on the homework, the conditions for eta. I mean, basically, this is just, you have to remove this absolute value and consider this in terms of these singular values, right? For a one-dimensional A transpose A, we'll just give you the, all you'll care about is the largest or smallest singular value. I forget which one. Sorry, 1 second. Okay. So as you can see, also these different lines that are being plotted are different approximations that gradient descent is getting us to the line that is actually going to be fitting here. Okay? So does everyone see how the choice of eta matters and how it is not obvious that we will always converge? Like sometimes it'll work, sometimes it doesn't work, but it's like the details matter basically. Don't like just say, oh, I did gradient descent and it converged to something, because a lot of times in practice I see people, just run gradient descent, stop it after some number of iterations, and this is your answer. But that might not be the case. That might not be true, right? Because you have to make sure that your conditions for convergence are satisfied. So this is something to be thinking about. Any questions about this demo? We're good? Okay. So great. I want to do another demo later, but for now I will stop showing this. So last time someone asked a great question, which is like, yeah, you love least squares and you did this for least squares, but what about other functions, right? Least squares, we already have the solution, so what's the point? So how do we generalize? And how can we say, something general for a general function? And so there's a large family of different kinds of results about gradient descent convergence. And you can kind of think of the lecture from this point on as an ad for 227C. Or 227C compressed. This is like the teaser lecture for 227C. So we're going to do some slightly advanced stuff. But if you really want to go into the details of any of this, that's the class to be taking. If we have time at the end of the semester, we have some open lectures for optional topics. I might try to give an additional lecture or two on this topic, depending on kind of how we end up. And we are trying to probably have a final project that also allows you to explore some of these different descent methods. So there are options to kind of explore further if you want to go in this direction. So we're going to talk about convergence proof for gradient descent for strongly convex or mu strongly convex and L smooth functions. Okay, so we've already defined strong convexity. Let me just remind you what this is. Mu strongly convex means that, for every x comma x prime, you have that f of, maybe I shouldn't use x prime, let me use y. F of y, and this is obviously belonging to the domain. F of x plus gradient at x, y minus x, plus mu over 2, y minus x, whole squared. And I'm thinking about vectors in general. Okay, so we've already talked about mu strongly convex, and we've thought about mu strongly convex as well. If I have my f of x as something like this, mu strong convexity means that there is a quadratic that I can kind of fit into, right? This is saying that there's a lower bound for the function that is a quadratic, okay? And this condition we are going to use to show that our gradients for our function are changing fast enough. So we want to basically be able to prove that, let's say this water bottle is my optimum and I'm trying to get to it. I want to take steps with gradient descent that will come close to here, right? But if I have gradients that are tiny, 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 they're not changing very much at all, then how am I ever going to get here, right? If my every gradient step just makes me go like very, very small nudges, it's not going to be at all useful. And so to be able to prove convergence, you need some kind of guarantee that your gradients are kind of doing the right thing. And that's what this is going to give us. The other thing that we want to have is also a notion of making sure that my gradients are not changing too fast, right? Because if I had a gradient that was changing really, really fast, one step might take me like all the way to the door, the next step might take me back to Quarry Hall, the third step might ping pong me, I don't know, all the way over to Strata, who knows where we're going to go, right? So you want to have both a lower bound and an upper bound for convergence. Does everyone see why we might want something like this? Like, is this intuition clear? Okay, good. And so here we're going to say that we are upper bounded by a quadratic. So we're going to say for every x, y in the domain, I have that f of y is less than or equal to f of x plus gradient of f of x transpose y minus x plus L over 2 y minus x squared. And what this L smoothness is talking about is saying that there's also, okay, I'm drawing this picture as a cartoon. This is not an accurate, very accurate picture, but that there's also a quadratic that's kind of above your original quadratic function, okay? And this red thing is the red thing. And this we want to say is that gradients are not changing too fast. Okay? Okay, I'm going to risk this. Let's see. Hopefully it'll come back down for the second demo. So using question.
If we don't know, like this whole thing is going towards we don't know the solution to the function, right? Like we don't know the optimal solution.
Mm-hmm.
And so if we want to prove convergence, is it that we have to prove both conditions, like both functions do converge, and then we know that the sandwich function converges?
That's a way of thinking about it. That's not exactly the way we're going to do. We're going to prove directly that the function converges using the fact that it has an upper bound that we know will converge and a lower bound that we know will converge, kind of. Basically, what we're saying here is that, yes, our function might not be a quadratic, but for all intents and purposes, it's kind of behaving like a quadratic. That's what these two conditions are telling us, okay? And we're going to get an exponential convergence here from this setup, kind of like the same kind of exponential convergence that we got here. One thing I had a question about this. This is a little bit trippy, but exponential convergence, so when you have basically an exponent, like something like alpha to the k here, is often called linear convergence. It's called linear convergence because when you make a log plot, you have a straight line, okay? So I feel for a first course, it's always easier to just say it's exponential because it looks like an exponential. So we're going to call it exponential convergence, but textbooks and other jargon will often refer to this as linear. So We're never going to test you on the terminology of this. We're just going to test you on whether you get the algebraic expression right, so don't worry about the terminology. But for now a function that satisfies this kind of setup, what do we want to prove? We want to basically prove a theorem of the following form, right? Let's say I want to find the min of some function f of x over, let's say, x belonging to Rn, right? Let's say f is an unconstrained function, so it's going from Rn into R. Let x star be the optimum point. Then I want to look at the distance that I am. Let's say that at time t plus 1 minus. Okay, so I'm saying at my t plus 1th iterate of gradient descent, right? Remember, what is gradient descent doing? X t plus 1 is equal to xt minus eta times gradient of f of xt, okay? Then I want to say that I can choose some eta, right, such that this thing is less than or equal to some constant c to the power t plus 1. And here in the vector case, it'll be a matrix, times my distance from the optimum at the original point, at the initial point. Okay? I can choose eta such that this is true. So I start out at this distance from the optimum. I can choose an eta such that this thing is going to be smaller than 1. And I'm going to basically have my distance to the optimum shrinking with every time step. And therefore, in the limit, as t goes to infinity, xt will converge exactly to x star. This is the kind of theorem I want to prove. Is everyone clear on the type of theorem I want to prove? Right? Another way to prove this directly, like this is one way of showing basically that limit xt as t tends to infinity is equal to x star. Right? Once you have this, this is immediately follows. So this is one style of proof that we can use to show this. Other cases, in some gradient descent algorithms, you might just directly take the limit of the xt's and show that they converge to x star. You don't have to do this kind of distance from the optimum kind of trick. Okay? Yes, question?
So just to make sure I understand, this theorem isn't true for all f. We're just saying like this is a theorem format.
Great, excellent question. So saying we want to be able to prove a theorem of this sort. This theorem is not true for all f. We are going to prove this theorem for f's that are mu strongly convex and L smooth. And as you might have guessed, our choice of eta is going to depend on the strong convexity and the smoothness parameters. Other questions? We're good? Okay. Wonderful. So to do this, what we're going to do is we're going to basically take this and kind of manipulate this expression to be able to get what we want. Not that different from the least squares proof. But first, we're going to prove some lemmas that help us kind of characterize how the gradients are changing. Right? I'm claiming, for example, that L smoothness tells you that the gradients aren't changing too fast. Let's make this even more explicit. So if I have an f that is L smooth, then I want to prove that the gradient of f of x is always less than or equal to 2L times f of x minus f of x star. So what this is saying is if I have this L smoothness property, I can directly interpret this to give me a bound on the gradients, depending on how far away I am from the optimum point. Okay? So what it's saying is that, look, if you're very, very close to the optimum, right? If f of x minus f of x star is pretty small, then do you want to be taking giant steps? Probably not, right? You probably want to take small steps, and so your gradient is small. But if you're very far away, then maybe larger steps are okay, and gradient descent will allow you to do that, okay? So what this is saying is it's saying as a function of how close you are to the optimum, your gradient is bounded, okay? And does everyone see how this is a way of saying that your gradients are not changing too fast? Okay, so let's actually prove this, okay? So let's say we're, proof. Or do you want a minute to think about how we might prove this? Sure, take a minute. Feel free to discuss with people. Okay, so that's a minute. I timed it. There's a little bit of a trick here. Like, it's not obvious where to start. So this is the key kind of thing to consider. So basically, think about starting at some point. Let's say you're at some x, and you take a step, basically like a gradient descent type of step with step size equal to 1 over L, and you end up here, right? So we're going to use kind of the L smoothness relationship between these 2 points to help us get where we want to go. So we know here that f of x star is the minimum, right? So that means that for these 2 points that we're going to consider, we know that f of x star had better be less than or equal to f of x, And it also had better be less than or equal to f of x minus this gradient divided by L. And both of these things are true simply because we've assumed that f of x star is a minimum, right? So it's the smallest value. If one of these was smaller, then that would be the minimum. But f of x star is the minimum, right? So we have both of these inequalities. Okay. Where should I write? Okay, I'll just keep going here. So we have this L smoothness condition that connects kind of 2 points at x and y. So I'm going to choose this y to be equal to this thing, okay? And I'm going to write f of x minus the gradient of f of x divided by L is less than or equal to f of x, just this copying this term, plus the gradient of f at x times y minus x, right? And so what is this y minus this x? Yep, so it's just negative gradient f of x over L, right? Everyone see that? Plus L over 2 times derivative gradient f of x over L squared. This proof is not particularly one of these insightful, like, oh, this is how, here's an intuition for how to proceed kind of proofs. Like, it's just some algebra. Yes, question?
Can you explain intuitively the meaning of the lemma again?
Yeah, I can explain intuitively the meaning of the lemma again. What we're trying to show is that our function isn't changing too fast, right? We want to basically say that when you're close to the optimum, you're going to be kind of taking small steps to move towards the optimum. So what this is saying is that, this gradient, the step you're going to take is going to be proportional to the size of this gradient, right? So you want to have gradients that are small when you're close to the optimum, and you want to have gradients that are that are larger, or you're okay with gradients that are larger when you're far away from the optimum. So that's what this is trying to capture. And this L parameter is basically capturing what that scaling is. Okay? Other questions? Okay, so from there, let me erase this. So from here, it's really just some algebra manipulation that I want to do to get to where I want to go. So I'm going to write this term over here again, f of x minus delta f of x divided by L is less than or equal to f of x. This thing is now just the norm of the gradient, right? Which is exactly the term we wanted. So it's minus norm gradient f of x whole squared divided by L. And here we already have the norm gradient. So this is just plus this L comes out, becomes an L squared, cancels with this L. So I get 1 over 2L gradient of f of x is just equal to f of x minus 1 over 2L gradient of f of x. Okay? Let me write this a little bit better. F of x minus this. So I have this quantity here. And now I basically want to connect, I want to bring an f of x star into this expression, right? I have this 1 over 2L times the gradient. That's kind of already gotten somehow engineered into my thing. So to bring this f of x star, I'm going to use this fact, right? I know that this is the function value evaluated at this particular point. But what can I say about the function value at the minimum point? It had better be smaller, right? So can I say that f of x star had better be smaller than this? Yeah? Therefore, I can say that f of x star is less than or equal to this quantity, right? And then rearranging we're done, right? It gives us exactly what we want. It's just an algebraic manipulation of this L smoothness condition. Like, this is like just a little bit of icky algebra that you had to get through to get to the proof. Straightforward enough? Yes?
Could you explain again why we know f of x star has to be less than that expression?
F of x star, why is x star, why is this true? X star is the minimum, right? So if the minimum value of the function is attained at x star, then it better be smaller than the function evaluated everywhere else. It's less than or equal to, we don't have a strict inequality because this might be the optimum point itself, but it definitely cannot be strictly greater than, right? It must be less than or equal to. Yes? Why did we take a step size of 1 over L here? Honestly, just to make the algebra work. I mean, we're not really taking a gradient step here, even we're just comparing these two values. And it's just a convenient trick to get this to convert. There's not really I don't have a smooth explanation for why one would think of this. You're just kind of rejiggering and playing around with it, and it kind of comes. Yeah, don't have a great intuition. Okay, good. So we have this. And let's do one more rearrangement of stuff that will help us. Maybe I'll just write it here. I want to also just rejigger this mu strongly convex and just write it, rewriting the strong convexity condition. To pull out basically this inner product. If I choose y in mu strong convexity, if I choose y to be exactly equal to x star, okay? So I choose y equal to x star, then I can rearrange that to write the following. Gradient of f of x, x minus x star is greater than or equal to f of x minus f of x star plus mu over 2 x minus. Sorry, I have a tendency to write the x stars as superscripts and subscripts both, but just I just mean the same thing, even if I write it up or down. Don't. So all I'm doing here is like rearranging these terms a little bit. Does everyone see that? Like I'm just putting y equal to x star and rearranging the inequality, and I get this exact expression. Verify for yourself that this is true in 1 minute. Everyone with me? I'm just writing this because it'll make things easier for me. Okay, so I'm going to call this, let's call this lemma 1. And this is not really a lemma, but let's call it lemma 2 anyway. Just because it'll be easier for us later. Yes? Should it be minus gradient on the left-hand side? I hope. No, it should not be, because I want to, instead of y minus x, I have x minus x star here. Yes? It is very possible I made an algebra mistake, but I don't think I did. Should be negative mu over 2. Okay, let's do it out. Maybe I made a mistake. Okay, sorry about that. So we have f of x star is greater than or equal to f of x plus gradient of f of x times x star minus x plus mu over 2 x star minus x. Okay? Right? We're good here? Okay. So now I have gradient of f of x transpose. So let's do this the very, very slow way. So then I have f of x star minus f of x minus mu over 2 x star minus x is greater than or equal to gradient of f of x transpose x star minus x. Right? All I did was I took this guy to the other side, and I took this guy to the other side. Yeah? Now I multiply everything by minus 1. So I have minus f of x star plus f of x plus mu over 2 x star minus x less than or equal to gradient of f of x transpose x minus x star. Yes? So this is the form that I want to use it in. So this thing is greater than this. So I want a plus here This is a negative term, this has a positive. So, okay? Good. Okay, good. Let's just keep this up here. Maybe I'll try using this board. No, I don't want to cover that. Okay. So, proof of main theorem. Okay? What do we want to do? We want to say something about the distance at time t plus 1 from our optimum. Okay? And we're taking, remember, our gradient descent algorithm, x of t plus 1 is equal to x of t minus eta times the gradient of f at t. This is our algorithm. So now I want to be able to relate this quantity to how close I was in the previous step, right? I want to eventually relate it to how far I was at x naught. But right now, first I want to just relate where I am at xt to where I was at xt minus, or xt to xt minus 1, or xt plus 1 to xt, right? So what is the substitution you're going to do here? Like there's one equation you have, and you want to connect xt plus 1 to xt. What's the substitution? Use the gradient descent step, right? Okay. I know this is a little bit of boring algebra, but it's just instructive to do it. Yes, like you know it's going to work out. You've seen the least squares proof. Not the most exciting proof in the world, I also agree. But it's useful to see it out once. So this is equal to this, so I'm just going to write that in. Minus x star. Okay? So this is just the gradient step. And now looking at this, I want to be able to pull out this xt minus x star, right? So I'm just going to rearrange this to write this as we're good here? And now I can think of this as a vector and this as a vector, and I can kind of expand this square out, right? So I can write this is further equal to xt minus x star whole squared plus eta squared gradient of f of xt whole squared minus 2 eta times the inner product between f of xt and xt minus x star. Okay, So we want to prove that this thing is getting smaller, right? It's getting closer and closer. So we want to say that this thing is less than or equal to something, right? Yeah? So we want to say that this is less than or equal to, well, we keep the first term as is. For this thing, do we have a lemma that tells us something about how the gradient behaves? It got covered up here, but we have this lemma 1, right? That tells us about how the gradient is going to behave. So I can write this is less than or equal to eta squared times 2L times f of xt minus f of x star. Okay? And now we want to say that we have this thing, which is this inner product between these two quantities. Let's just rewrite this inner product in a way that is matching that. I can write this as gradient f of x transpose times xt minus x star. Right? So what I have here, what the mu strong convexity is giving me, is something gradient of xt times, xt minus x star is bigger than some quantity, right? Here, I have the negative of that quantity, and I want to say that it's less than something, right? So basically, I can substitute in exactly this, right? If I have A is less than or equal to B, then I have minus A is greater than or equal to minus B, right? So just by doing that, I can write here 2 eta times f of xt minus f of x star plus mu over 2 xt minus x star. And now we just do some kind of rearranging, some algebra. We want to get terms like this, so we want to collect all of the terms that are of the xt minus x star form, right? Question? Okay. Yeah, no, I am definitely prone to algebra mistakes today, but I think I did it right. Yes.
So the main theorem is for all convex functions.
No, it is not for all convex functions. It is true only for mu strongly convex and L smooth. If you're only mu strongly convex, you won't be able to do this because you can't do this step, right? If you're only L smooth, you can't do this because you can't do this step. So it has to be both mu strongly convex and L smooth for this proof to be true.
How do you know what eta we're using? What we're using?
In 1 minute, you'll know the answer to that question. Good question. Okay. So rearranging, we have this term here, and there's also this same thing here, right? And you have this 2 eta times mu over 2. So I get basically 1 minus eta mu times xt minus x star squared, right? And then plus, I'm going to collect all of the coefficients of this term here. These blue terms match. And so there I get what do I get? I get eta squared, or 2 eta squared L minus 2 eta times f of xt minus f of x star. Right? Just some algebra. I think I did the algebra right, and it matches what I have written here. So odds are that between last night and today, unless I made the same mistake last night and today, it's just possible. I think it's correct. So now I wanted to, what was the theorem I wanted to prove? I wanted to prove this is some factor times this, right? That's what I wanted to show. And I have this is some factor times this. But I have some junk lying around here, right? What would be great if we could just wave a wand and make this go away, right? That would be awesome. If you just make the second term go away. Can we make the second term go away? What is the one thing that we have control over that we haven't used yet? Eta, right? So now, what eta do you want to choose? You want this thing. If we could make this equal to 0, then we wouldn't have to bother about it, right? At all. This would be this nice property that we wanted to have here. So choose eta equal to 1 over L. This implies that 2 eta squared, or basically this is 2 eta times eta L minus 1 is equal to 0. Which implies that this thing is less than or equal to 1 minus mu over L xt minus x star. And then recursing that, I get that the norm of xt minus x star squared is less than or equal to 1 minus mu L to the t plus 1 times my distance from x naught. Which is what I wanted to show, right? So as long as this quantity is less than 1, I'm set, right? So I can choose an eta such that this is true. And this is always going to be less than 1, because remember, the L is the kind of the L is the Hessian of the quadratic that's on top, and mu is the Hessian of the quadratic that's on the bottom. So the steeper one always has the higher coefficient. So mu is always going to be smaller than L. Okay, so this shows that basically whatever you have for least squares was not a fluke. This works generally, and you will converge exponentially fast, or you will have linear convergence, depending on how you choose to write it, to your optimum point. Okay? This is now holding true only for these special functions that are both mu strongly convex and L smooth. I'm not going to expect you to memorize and reproduce this proof, right? This is, to some extent, a large amount of just algebra tricks. However, I do expect you to understand and kind of know the spirit of the proof, right? And doing a calculation in this flavor and trying to understand kind of, how we're trying to compare, showing this idea of a convergence proof, like showing how xt might converge to an x star, is something that I want you to take away from this. And then you have an example here, and then you have some other examples on the homework, as well as some, the one that you'll see in discussion. So this now explains what you see in terms of behavior for the example we saw. Exponential convergence is really quite fast. This, however, is, OK, sorry, I should pause. Questions? No questions. Good. This is now something that holds true for these special functions, in a sense, that are both mu strongly convex and L smooth. But that might not always be the case. So for example, you can go on to prove other convergence results. We're not going to. But if you had a function such that it was convex, and all you knew about it was that it was L smooth. Okay? Then what you would see is that you could get a convergence that's of order 1 over t. Okay? So you will converge slower than what you might if you also had mu strongly convex. Because mu strongly convex is basically saying that, once you're kind of getting close, sorry, let me think about this. That's saying basically mu strongly convex is giving you some guarantee of how fast you're going to converge. You don't have that guarantee, your convergence rate is going to go down. Okay? There are other kinds of convergences. If you have other properties about the function, such as Lipschitzness, you can prove different kinds of things. Vanilla gradient descent, for a non-convex function, of course, you're not going to have any kind of guarantees there. You might get to some local minima. You don't know. If you're interested in doing a lot more, analysis on these kinds of things, take 227C, right? The entire class will talk about different variations on gradient descent and how they converge, when you might want to use them, different things like that. A good reference for this is the notes by Bubeck, which are excellent. And so if you want to read more about it on your own time, that's also something you can look at. But what I want to do with the rest of the time is not go through more convergence proofs, but just kind of give you a sense of where to go from here. Gradient descent is just the beginning, it's the foundation, right? But gradient descent is one algorithm, and basically it's the basis for many, many, many variations that you have on this particular algorithm. One very common variation that is often used is this idea of stochastic gradient descent. So how many people have heard of this particular thing? How many people have a good understanding of it? OK, so what I want to try and do is kind of, because of how popular stochastic gradient descent is, I want to give you a sense for what this algorithm does and how it compares to and is a modification of gradient descent. We're not going to go into a convergence proof for stochastic gradient descent. It's definitely, I wouldn't say it's out of scope. I think we could do it, but it would be like 2 or 3 lectures worth of material to do it well, and we don't have that kind of time. But if there's overwhelming demand, we could maybe fit it in at the end of the class, okay? But I want to just give you this introduction to stochastic gradient descent, and if we have time, I'll also tell you about projected gradient descent, which is the idea of what do you do when you have a constrained set. So not that you are having an optimization that is unconstrained and you can go anywhere in your vector space, but you have a constraint that you're restricted to. Stochastic gradient descent. So stochastic gradient descent relies on this idea that often what you're doing in the function that you're minimizing is you're thinking about some kind of loss function. And this loss function is being evaluated at many different points. So for example, if you're trying to minimize some f of x, right, over some x belonging to Rn, for example, quite often, for example, in the case of least squares, but in many, many other machine learning contexts as well, your f of x is of the following form. It's I going from 1 to m, basically. It's the average of losses at different points. So basically, I'm saying, let me look at the loss. My function can be thought of as this sum. Okay? And to see what I mean by this, just as an example, for example, for least squares, if I have my losses, typically we think of it as ax minus b squared, but I can also write this as a sum, right? If I think of A as being given by A1 transpose all the way up to AM transpose, let's say, then I can write this as I going from 1 to M, AI transpose X minus BI. Right? Everyone see this? So basically, this is saying that for every kind of data point, right? Basically, one row of my in my least square setup, every row is an experiment. Every row is a data point, right? And this is saying, let me sum the loss on the first data point, the second data point, the third data point, and I'm considering the average of those, for example. In this case, for example, you could write this as 1 over m or 1 over 2m, which is often a convenient scaling just to make some of the constants disappear. But from an optimization perspective, it's all kind of fine. The 1 over m scaling is something that you will often see or for gradient descent or for stochastic gradient descent settings because you want your loss to not care about the number of points you have. So basically, by having this normalization, your loss is the same if you keep getting more and more data. You can compare losses with more and less data, okay? Because you're dividing by the number of points. So I want you to keep this kind of thing in mind when you're thinking about stochastic gradient descent. So why would we consider some variation on gradient descent? Stochastic gradient descent is a modification on gradient descent that is specifically thinking about the case where evaluating the gradient or having access to the full gradient at every time step is too costly. So if I have basically m data points, right, I had to do order m computations to be able to get all of this, this loss function, right? Or to be able to compute the gradient, I had to do basically A transpose times my entire vector, right? So I have a lot of computation that needs to be done there. Instead, if what I could do is I could say, well, let me say I have access to a much weaker notion of the gradient. And I'm going to say, let's say this is eta k times the gradient of fi at xk. So instead of looking at the gradient of all of f, I'm going to say, let me just choose one component. Let me just choose one particular point. Let me just look at one particular row of least squares and look at the gradient of that. Okay? And can I make progress by doing this? So one nice thing to note is that in this case, I won't prove it here, maybe we can do it next class, that the expected value of this quantity is exactly equal to the gradient. So when you take a step of a stochastic gradient descent algorithm, in expectation, you're moving in the direction of the gradient, but actually what you have is some amount of noise. Question?
Are we randomly selecting an element? Is that what
Yeah, you basically would say that you're going to randomly select an element, and if you choose select uniformly at random, that's a one-line proof there. Good. So I don't have enough time to go through the entire example. Let me show you one quick thing. Okay, let me show you this. While that screen is coming down, let's see this in a very, very simple example. So let's say I consider the example where my f of x is equal to 1 over m, 1 over 2m, sigma x minus pi whole squared. So I have a set of vectors p1, p2, pm, and my loss is basically my distance of x from all of these vectors. What is the solution? What is the x that minimizes this? I want to be close to p1 and p2 and p3 and p4 and p5. This is the average, right? We know what the solution to this is. You can check, and maybe we'll do this next time. Maybe you can do it as homework. If I choose my step size, not a constant step size, but I choose it time varying, so eta k is equal to 1 over k. X naught is equal to, let's say, 0. And you choose, first you choose the gradient of 1, and then you, like first you choose the first term, then you choose the second term, then you choose the third term. Stochastic gradient descent will get you exactly to the right spot. Okay? We don't have time, unfortunately, to do this, and I'd rather show you this quick simulation so you can see something more visually. So what we have here is an SGD implementation here, a gradient descent implementation here. Again, we're doing the exact same thing where we have a bunch of data points, and we're just trying to fit a line, like the exact same demo that we did at the beginning of the class. What you see here is I'm taking SGD of this data with step size equal to 0.1, and I'm running for 1,000 iterations. And this is like just going on and on, right? It is not really converging. It's getting, it's doing, but it is doing something reasonable in the sense that my true x is 3, and it's kind of getting somewhere, right? If I choose, let's say, a smaller eta, it's doing something. It's like, it's not, like SGD works in practice, right? It's doing something reasonable, even though you have a very, very weak notion of the gradient, right? Like you're only on average moving in the right direction. Like many, many times you're going to move in the wrong direction, but this still works. Compare this to gradient descent. So let's use the same step size that we used on SGD here on gradient descent. And I've converged in like 10 iterations. Here it's taking me like 500 to even kind of get in the same right ballpark, right? So SGD has much less information about the direction you should be going in, and you pay by taking more time to converge, right? But every iteration, every step is less computationally intensive because you're doing, only the computation for one data point as opposed to for many data points. Okay, so a quick vote. How many people would like for me to spend a little bit of time talking about maybe like 5 more minutes on SGD and a few other variations of gradient descent in Tuesday's lecture? Or how many people would like me to just focus on like things like the SVD that are more directly useful for the exam? We're not going to ask you a question on SGD on the exam. Like, I'll already tell you this, right? How many people want gradient descent, SGD, or projected gradient descent type things? Raise your hand. How many people want me to focus on the SVD or principal components? Great. Way to be 50-50. Okay, I'll try to do some averaging of the two. See you Tuesday.